This video is I'm going to talk about fatigue failure. This is chapter 6 of Shigley, and I'm going to try to go through this relatively quickly because I've been here for past my quitting time. All right, the thing to start with in fatigue is the SN diagram. What the SN diagram essentially does is plots out a line on a log-log graph. So to start with, we have this graph right here, and we're going to have 3 points that we really care about to be able to create an SN diagram, or simply to be able to understand what it's actually doing here. The 3 points are at n equals 1. That means like one cycle. Obviously, that just means that you're just put the load on. It fails at the ultimate strength. Okay, that just makes sense. Okay, so it's 10 to the 0 down here in number of cycles. All right, the next point is going to be when n equals 1,000, 10 to the third. Well, this isn't exactly on this graph right here, but that's pretty much understood to be 10 to the third, and that's considered low cycle fatigue. We're not going to concern ourselves with that section. Just know that anything below 1,000 cycles is low cycle fatigue and does not behave in the way that we're going to look at things. And the next point, the last point that we find, is going to be equal to at 1 million cycles, we find it becomes an endurance strength. Now, okay, this is only for steels, but steels have a strength, the endurance strength, SE, that if you stay below that, it predicts infinite life. Okay, so that's the point we found here. How do we find this point up here? We apply a factor, this F times the ultimate strength. We find that F from this figure right here that's in the book right here. So you find the ultimate strength right here, and you go up and you find that F. Now, buried within the text, note that if your ultimate strength is less than 70, you just go ahead and use 0.9. You don't extrapolate up. All right, so we were able to take that F and multiply it by the ultimate strength and be able to find that at this point here, that's going to be that SF. It's not a very good variable to use, but that's what they use in the book. Okay, so we found that point, and we find this point at 1 million cycles. Sometimes they said 10 to the 7 as well. It'll be in the book. It's not consistent. So what happens, the way that this line gets created, is you make really it's a logarithmic straight line, which you have a factor times here and a coefficient. Well, I should say a coefficient right up here and an exponential right here, this a and this b. And the way to find it, if you did a little bit of math, it would find that the a was going to be that F times S, the ultimate strength, squared, divided by the endurance strength. That's this guy right here. So I'll go ahead and label him. He's the endurance strength, SE. And b, which is the exponent up here, is going to be b equals to negative 1/3 the logarithm of this ratio right here. Make sure that you notice that this part right here is squared, but this part is with the logarithm is of this entire thing. So don't get that mixed up. Also, a bit of warning: A and B get reused in the same chapter, so that's very confusing. Don't be mixing them up. This A and this B is only for this equation right here. And a more useful version of this equation, just rewritten, is the number. If you wanted to find the number of cycles, you get this completely reverse stress divided by this A raised to 1 over B. Okay, and what that gives you is within this limit right here, if you know the number, or excuse me, if you know the stress right here, if you find the reversible stress, you go across, find the intersection, and come down, and that'll give you the number of cycles that's predicted to failure. This is not a precise prediction. It's really an estimate. So when you give the answer, don't give more than 2 sig figs. You might not even want to give more than 1 sig fig, honestly, but 2 sig figs is probably how we're going to handle it. Don't give 3, 4, 5, 6. Don't give me a lot of numbers. You just want to give 2 sig figs for this. Now, we have some questions about how do we get this endurance strength right here, because we know the ultimate strength, so we get that point, and we know this this point right here is just that F times this factor times the ultimate strength. How do we find SE? First off, before we move on to that, I want to make this very clear. This diagram right now, if we didn't do anything, if we didn't specify anything differently, is only for completely reversed stress. Okay, that's an important thing to remember. Completely reversed stress. We'll see why in a couple of slides. All right, first, how do we find that endurance strength? What we do is we apply some modifying factors to an ideal specimen to convert. In our ideal specimen, we're going to write SE prime. Okay, so it's that prime means that's an ideal specimen. It's a specimen that's in bending only, completely reversed, and is highly polished. Okay, so it's almost like a hypothetical thing. It's like a laboratory specimen, perfectly done. All right, so you find that SE prime for a carefully prepared and tested specimen. And if you could possibly do it instead of doing, this sentence is really kind of out of place, but if you had a testing of the actual parts and you were able to do the actual parts on the actual loading of all the actual things that could take place, you would find an SE without doing this modifying factors and stuff, but you basically never have that situation. So instead, you're going to apply a bunch of modifying factors onto this SE prime, all right? And the SE prime is generally, because we don't have a better number, we're just take this really rough estimate. So this is almost what we always do, and take 1/2 the ultimate strength. Okay, I know that seems kind of arbitrary, but it's just a gross estimate, and that's generally what gets done. Now we take this SE prime and we want to turn it into SE so we can use it on our graph. And we do that with this so-called the Marin factors. Now these Marin factors include the surface condition, because if the surface is rough, that's going to cause it to fail quicker, right? You can have a crack that propagates from a rough surface. And so that you need to degrade this SE prime by the fact that it's got a rough surface. Instead of a polished surface like a test specimen would have. The size factor, if you have a different size than than a standard test specimen, if it's larger or smaller, you need to correct for the size. So that's a KB. A load modification factor, that's if you have a different kind of load scenario. If it's a non-bending scenario, you need to account for that, if it's an axial or if it's in shear. If you have a temperature that's extreme, whether it's a really high temperature, I think even if it's a really low temperature, you apply a temperature factor. If you want a reliability that's greater than what is normally assumed, and I think the reliability that's assumed is something like 50%. So if you want a higher reliability, you have to apply this reliability factor. Then they have this catch-all miscellaneous effect. We won't use that for anything, but that could be applied, but we basically won't ever use it. We'll just keep it. So like if any of these things doesn't come into play, you treat it as equal to 1. Okay, so we start out with this 0.5 times the ultimate strength for this guy, and then we knock it down with each of these factors that we multiply it by. One thing to be very careful about is this is a lowercase k, even though it's hard to tell here when it's in Times Roman, and I will draw it like a lowercase k. And make it even more complicated, some textbooks will include inside here a stress concentration factor. We do not, and this is lowercase k is not a stress concentration factor. We do that separately. We apply the stress concentration factor to the stress, okay, not to the strength. So the stress concentration for this fatigue is found in the same way that we normally would. We would go up to the appendix and find KT, which is the theoretical stress concentration. So like, for instance, when you had a little hole right here, you found the diameter of the hole compared to the width, and you did like a little ratio right here, the D to W, or right here, and you found your KT. It was some curve like this right here, and you would find this value of KT for that ratio. And if you want to apply it to the stress, remember that you have to use only the area that's right here. You don't want to use this area right here. No, that's not good. You have to use the remainder area to find that. But before we get to that part, in fatigue, you have to downplay this theoretical stress concentration factor using the notch sensitivity, this Q, notch sensitivity. Q is dependent on the material, right, and is a little bit different for shear, so there'll be a different graph to look for. That graph is this right here. When you take your theoretical stress concentration factor, big capital KT, that you got from the appendix, and you subtract 1 from it, multiply it by the Q that you find from this, right? So you get the notch radius of the thing. So let's say that it is the hole in a plate that we're talking about. Well, this is the diameter. Make sure you only use the radius for the thing. Find it right here, and you figure out what the ultimate strength is of the material. And let's say it's this guy right here, and you come over and you say, oh, okay, that's going to be like 0.8, I don't know, that's like 0.825 or something, and you put that into there, and so it reduces this theoretical stress concentration, because some materials aren't as sensitive as others to that having a notch in there. Now, another thing that we have to compensate for is the fact that this is a fluctuating stress, okay? And that the fluctuating stress might not always be exactly completely reversed. Completely reversed means that like the tension that maybe comes up here at its maximum is equal to the compression that happens at its maximum. So it's going back and forth. It's always perfectly fluctuating, right? So there's the completely reversed down here. But sometimes it might like go to a maximum and then go to 0. And then a maximum that goes to a 0, or it might have something where it never crosses 0. It's like in tension and then less tension, and then back to that greater tension, then less tension. So that's like a general fluctuating thing. And so the repeated right here, that just means that it goes to 0 every now and then, or it goes to 0 as it reciprocates. So we want to talk about the mid-range stress and the alternating. Sometimes I think of this as mean or average. You got to be careful, because that A might lead you to think that's the average stress. That's the amplitude right here, right? So this amplitude is this guy right here, this stress, and then this mean is right here, or the mid-range stress right here. So you want to try to, I know it's simple, but you want to keep these straight, because what we really want to do, we're going to try to account for the fact that this is there's an alternating and a mid-range, and it isn't completely reversed. If it's completely reversed, then the mid-range is going to be 0, right? So that makes sense. So what we want to do to try to compensate for this is plot the alternating stress versus the mid-range stress, and we will try to convert it into completely alternating stress. That's the whole point of these graphs. So we have a bunch of different lines. These are different like theories on how to go about this. First off, if you want to go from yield to yield, that's often called the Langer line. Now, this is really just, if you think about it, if it was non-alternating stress, it was a completely just mid-range stress, that would just be a static stress that was applied to this. Sometimes this is called the static line, right? So that would be along this horizontal right here, and it would make sense that the thing failed by yielding along that line, right? So that would be one of the criteria. So that's the one to look at. There's the area underneath it. I don't know why I'm putting that there. Now another one to look at, we want to plot, this is called the modified Goodman. Well, why is it the modified Goodman? Well, I don't know this for sure. Instead of using on the alternating the yield as the criteria, it makes more sense to use the endurance strength on the alternating axis right here, on the y-axis. All right. So, but because the endurance strength means that the thing, like, you know, if it was higher than the endurance strength, and it would break completely. So it makes kind of sense that you would also compare it. If it's gonna, if breaking is the thing it does, then it's really the ultimate strength that you want to have on here, right? So like that you have these two things connecting. So that's I think of this as the Goodman line, and then by modified Goodman, we say, hey, at this point, yield is kind of a bad thing too. So maybe we don't want to allow it to yield. So maybe the modified Goodman is going to be this line right here up until it gets to this point where they intersect, and that and the bottom line is we want to stay underneath this line of these curves, right? So I consider that the modified Goodman. All right, now another one to do is a very conservative one called the Soderbergh line, and this is a very common one to use, where we connect that endurance strength to the yield strength. And you can see that there's going to be a region in here that could possibly exist where it would be okay according to modified Goodman, but Soderbergh would say it was no good. So Soderbergh is very conservative in that way, right? Now we take a couple other ones that get used in certain industries. There's this Gerber line right here, and that's the line of this forms a ellipse, I believe, or parabolic. It's written right there. I should read it. And that's one. And then another one is this ASME elliptic. Oh, that's where I thought about elliptic. Okay, it doesn't look spelled right. Maybe it isn't. All right. And it's used in other criteria. Probably the ASME would think that their line is the best one. The thing about the ASME and the Gerber that you might want to keep in mind, they might be a superior or maybe more accurate criteria to account for alternating and mid-range, but they're harder to use mathematically. So in most work that we'll do, we're going to stick to Soderbergh and Goodman, and then when we're done, we'll check Langer. So that's really the thing we do. We use Soderbergh and we use Goodman, modified Goodman, and then Langer is always a check afterwards, because if the thing fails in the first cycle, if it yields, that's bad, right? So we always do that as a little check. So the way to approach this in the criteria quite often is to take a load line. That is, you find the calculated stress that you have right here, and you plot it onto the horizontal axis, and then you find the alternating and you plot a point, and then you plot a point through zero through that line right here, and this is your load line. And now the intersection of this load line with each of these different lines, that's going to form a safety factor. So it looks a little, it's graphical type of thing, and we could also kind of spend a lot of time looking at the math behind it, but it's done in your textbook. The bottom line is that you're going to have a bunch of safety factors. It's called Soderbergh. You'll have the Goodman. I'll usually do this right here. You'll have AMSE, and then you'll have the you have the Langer too. Sometimes I go Lang on top of that, and then you have the Gerb, I call, right? So, and you could look up these equations in the text and just plug in these the factors, that the numbers that you need to be able to get these safety factors. But what they really mean is how far away your point is from the intersection of their line. It's how far you're away from being bad according to them. Now, another thing that is of interest to us is when we find a point like this, okay, and we want to try to project with, let's say we want to project what this is actually a bad example because it lands right on our line. But let's say that we had a point like right here, okay, that'll help us out, and I'll use another color to make this clear. Let's know. Again, that's not the color. Right, here we go. All right, I'll use another color. Purple's nice. Let's say that this is our point right here. And yeah, okay. We want to estimate the completely, because right now this has both mid-range and alternating stress, but we want to see what would this be in completely alternating stress. Okay, first off, I want to point out that just because it has a safety factor below 1 does not mean it's necessarily bad. What that means is on your SN curve that you had, right? We had this SN curve. It means that it is not going. We're not predicting infinite life. So if one of these numbers, not this one, but if one of these numbers is less than 1, that means that it is not going to survive infinitely. So it's going to land somewhere over here. It could be in low cycle too. Just be aware of that. But we're looking to say now, hey, it's not going to live forever. And now the question becomes, well, how long is it going to live? Well, what you do to do that, one way of estimating it is, if you decide to base it on the Goodman line, is you take from the ultimate, right, because we're basing on Goodman, and you draw a line through the point right here. Okay, this is not a very straight line, but you draw a line through this, and the intersection right here is what you're predicting. That's the conversion to the completely reverse stress. Okay, and you could do that with an equation. It's within an example in your text, and it'll show you how to do that. So that's the big idea here. If one of these is less, or the one probably Goodman is less than 1, right? Then you say, okay, and by way of this point being higher than Goodman, that means, okay, yeah, because you obviously, if this was less than Goodman, right, if it fell underneath the Goodman line, it would be something less right here that it would go through, and it wouldn't matter because now it's going to be something less than the endurance strength. So anyway, let's do a little example here quickly. I take this bar and I'm putting it through a 800 to 300 pound fluctuation, and it's 3/8 inch thick, and it's got a little 1/4 inch hole in it, and it's 1 inch wide. And if I want to estimate the safety factor guarding against failure because of fatigue action, so you find the alternating and mean stresses. That's not what I did right here. Okay, I found out what the area was. Okay, you got to be careful and use the correct area, right? From the equations. Okay, now this is where I find the mean and alternating stresses. You take, the alternating is going to be that negative absolute value of this, by the way, divided by 2, and then the mean is going to be, without the absolute value, is going to be the max plus the min and divided by 2. Makes sense. And so you find the stress right here. You take that alternating force and this mean or mid-range force and divide it by the area. Make sure you use the correct area. Now you look for notch sensitivity, and if you look for the notch sensitivity, by the way, notch sensitivity is not only on that curve that we looked at before, where it went up to 0.9. You remember that 0.9? No, that's not true. Sorry. It was the curves that went like this right here. Yeah, there you go. And you found based on the radius and the material right here, and you're able to find a Q, right? Well, you can also find a Q this way using this big ugly equation. Well, what's nice about this is that, like, if you're doing a computer program or doing an Excel spreadsheet, you could plug this into here, and you wouldn't have to go looking up for the graph, at least in this instance. All right, so that we could plug this in right here, and we could change what we find as our stress concentration factor in the back of the book, and it gets knocked down by this number right here, by the not sensitivity. So apparently in the back of the book it's 2.42 is the theoretical stress concentration. And so if we do that and we take this KF, we can apply it to both the alternating and the mid-range. I'll point out that there's a section in the book, a page in the book, I'll get the page number to you at some point, that says that you apply it to the alternating but not the mid-range. There's some caveat as to when you should do that and when you shouldn't. Be on the lookout for that. see, what are the material properties? That's the next thing. Once we found the stress, now we want to find the strength. That's sort of the theme that we find a lot of times in machine design is we compare stress to strength. So we found the yield, of course that's supposed to be a Y there, is 54 and the ultimate is 64. So the what we do first is we find the non-adjusted, that's the SE prime, 0.5 the ultimate, which is there. So it's 32. So we start out with 32 and now we're going to adjust it with these factors right here. And our specimen, the surface, by the way, you got to be careful of that A and that B. Those are not the same A's and B's that we used on the line and the SN curve. Those are totally different. This is the surface condition factor, not the same thing. Be very, very careful. I don't know why, but they use an A and a B here, and it looks very similar, right? But you use this to adjust for the surface condition right here, and you could look it up in a table of when to use what coefficient. And then the size, well, the size didn't matter. You have to look in the text that says, hey, when you're in this condition, the size won't matter. But I think that's when it's an axial, the size won't matter. You won't apply a factor for it. And for the loading condition, well, the loading is axial, so use a 0.85. That's in the book. The temperature, reliability, and miscellaneous is all 1 because there's nothing extreme here. And you apply all these factors and you get something, the 24.39. Generally, these factors will always be 1 or less, okay? And you want to also make sure that you use this number right here is going to be less than yield. It won't make any sense if it is greater than yield, okay? So if we apply apply the equations that are for the safety factors, this is the one that's for the Langer, right? Where you multiply you add the alternating and the mid-range together, and then you take it as a ratio and say, okay, what is the yield strength compared to that? And then you take the Soderbergh and Goodman and Gerber and ASME, and make sure you look for the thing here. I think I might actually have this written wrong. I'm a little concerned about that. I think that should be it should be, no, I guess it's probably okay. Yeah, it makes sense. Okay, so I always question myself. So this Langer right here, it's going to be the most conservative, so its safety factor should probably be pretty high. Still a little concerned about that. Anyway, you fill in you plug and chug here. When we find the Soderbergh is 1.67. And the Goodman is 1.8, and the Gerber is 2.24, and the ASME is 2.35. Now we want to take a look at how that applies here, okay? There's the Soderbergh line, there's the Goodman line, there's the Gerber line, there's the ASME elliptical, and here is the Langer. All right, so I guess I see what happened here is because this goes to the yield right here, right? This is the capital S, yield strength right here. And it goes down to here also, there's the 54. There's the yield strength, right? So there, we plot a point right here, or we plot a line, I guess, or where's the point? Okay, here's the point that we found from our calculation right here. And here's the line that goes through it. So you can see the intersection, and you can see the numbers that came out, all right? So that was the one that I was looking at and going, I'm not sure if that's the right. But the Soderbergh was like the largest number, if you'll recall. Like look at the back up here, it was a 2 point, excuse me, I said Soderbergh, I meant Langer. The Langer is the largest one right here at 2.42, and that's just because it landed the way that this curve landed out, okay? It was over here onto the spot, but it makes sense. So it's a ratio of the actual spot, this spot right here, this length compared to this length right here, and that becomes what the safety factor is.